Hey everybody, we are going to do some notes for chapter 2, which is on atoms, ions, and molecules. And this information will be on the first exam. Looking at this, a lot of this information is review from your introductory bio courses. So this might be a lecture that you can sort of rush through more quickly, but it also might be one that you do need to spend some time with if it wasn't really solid for you in that like bio 101, 102 time. Of course, there are lots of resources and videos and worksheets and Quizlet and all of that for you on our D2L. So please feel free, utilize those resources as well as utilize me as a resource if you need some more help understanding. But let's just dive right on in. Here are the objectives. Again, I'm not going to read them to you, but they are posted here and in the D2L if you, want to spend more time. But pretty much these are the things the department is going to expect you to be able to do and to know by the time we get to the end of this section or this PowerPoint. So if you are feeling good about them even now, great. If you're not, stay tuned. We've got a whole bunch of stuff here for you. Let's first talk about matter. And this might be more of a chemistry, even physics sort of vocab word, but it's important for us too in biology. So matter is anything that has mass and takes up space. And we recognize that there are 3 states of matter for our purposes. When you go into physics, they'll talk about plasma and other things. But for us, we just really want to focus on a solid, a liquid, or a gas being the states of matter. So solids are things that have a definite shape and volume. They're usually pretty rigid or fixed, and they're not easily squashed. And if you are, at your desk or listening to this, looking at your computer, it's probably most of the things around you, right? It's the desk, it's the computer itself, it's all of that stuff in your living room or wherever you are. Most of it is a solid. Then there is liquid, and liquids have a definite volume, but their shape can change. So when we look at a liquid, it's not rigid, it doesn't have a fixed shape. If you are, drinking coffee or tea or water, and you pour it into a cup from a different container, it changed shape from being in that container into your cup. Okay, and it's another one of these states of matter that we say we can't really squish it. It changes its shape, so it's not compressible. And then a gas has a changeable shape and a changeable volume. So if you put a gas in a container, you can squish it. And gases are not rigid, they don't have a fixed shape, and they don't have a fixed volume. And, just in your everyday life, the air that is around you, that's gas, right? So again, our states of matter that we are going to focus on are solids, liquids, and gases. What makes up matter? Well, an atom is the smallest particle that is going to show chemical properties. And it's the smallest unit of matter. And if it's an element, then it's going to be a substance that is all the same types of atoms. So an element is something like aluminum or hydrogen. That substance that we call hydrogen or aluminum has all of the same types of atoms in it. There are 92 naturally occurring elements that make up matter. And you can remember back to any chemistry courses you've ever taken, even, like grade school chemistry, you probably saw the periodic table of elements. That is, where we organize and show the elements that we know of. Because we want to put these elements with their names onto the periodic table, scientists have come up with what we call the chemical symbol. And it's unique to every element. They each have their own. It's usually identified by the first letter or maybe the first and another letter. But we also sometimes use the Greek or Latin words for those elements to give them their chemical symbol. But it's basically just the letter that you see on the periodic table to identify that element. So, for example, C is for carbon. Um, Obviously, carbon starts with the letter C, but something like iron, that's going to be Fe, because the Latin word for iron is ferrous, so they used that instead. And again, each element has their own chemical symbol. And so here is a periodic table of elements. I'm sure this looks familiar to you. You do not need to memorize the whole thing and the periods and the rows, and don't spend time doing that. For me, if you're taking a chemistry course, that might be a thing. But we're really going to focus on these highlighted elements here. And these are some of the most commonly found elements in a human body. So we've got, of course, our hydrogen, we've got carbon, nitrogen, oxygen, sodium, magnesium, potassium, sulfur, chloride, where calcium and iron are going to be our major elements that we will use in this course. But still, again, don't feel you have to memorize these. So this is a graphic that comes straight out of your textbook showing you the most common elements in the human body. You might remember from your Biology 101, 102 courses, CHNOPS being sort of the way to remember the most common elements in living things. And I don't have a fun way to remember the ones specifically to the human body. So if you've got a cool mnemonic device, please share it with us. We all would love to know. But the major elements that make up about 99% combined of the body weight are oxygen, carbon, hydrogen, nitrogen, calcium, and phosphorus. Those are going to be the major elements. Then minor elements, they're still there, they exist, they're very important for body functions, but they're less than 1% of body weight, is sulfur, potassium, sodium, chlorine, magnesium, and iron. So now that we know that atoms are the smallest unit that make up matter, what does an atom itself look like? So we call that the atomic structure. And of course, we draw it out in this nice, nucleus in the center, rings around it with electrons. But truthfully, scientists don't know exactly what an atom looks like. There's been many, many models of atoms throughout history. You may have heard of like the cookie model, where it's like chocolate chips in the cookie batter representing the electrons. There's lots of models, but this is what we have now as our best guess. And we've got this nucleus, that's the center of our atom. And in that center, we will find neutrons. Neutrons are subatomic particles that have no charge. N for neutrons, N for neutral or no charge. And when we think about how big or how much mass it has, we're going to call it a one atomic mass unit is how much a neutron weighs, which is sort of an arbitrary number for us as biologists, but know that it has some substance to it. So we say it has one mass unit. Also in the nucleus, we find protons, protons have a positive charge. P for protons, P for positive. They also have a mass of 1 atomic mass unit. Then outside of that nucleus, we find electrons, and we say that they are orbiting in an orbital or in an electron cloud, but they are outside of the nucleus, and they have a negative charge. Um, there's not a good way really to remember electrons having a negative charge. Those words don't start with the same letter, but I like to think of like all of the little lines that you need to make all the E's and the T as a lot of little negative signs. So if that helps you to remember, use that. If that confuses you more, just, throw that bit out. But electrons have a negative charge and they are very, very small. So we don't assign them an entire mass unit. It's 1/2000th. Or for the purposes that we have in biology, we just say they don't really have a mass. It's 0 because they are so, so small. So, on our periodic table, we want to share some of this information because we need it to understand how chemical reactions within the body, within the world, are taking place. So, when we look at an element on the periodic table, there's some very important parts. Oh, sorry. There is first our atomic number. Atomic number is going to tell us the number of protons that are in the nucleus of that atom. And it is the number that is right above the symbol for that element. So here for carbon, our friend carbon, if we look, C for carbon, C is that symbol. And then we see this number 6. And that number 6 is our atomic number. It tells us the number of protons. And again, protons have a positive charge. In a second, we will see that if we know the number of protons with that positive charge, we also know the number of electrons because it has a negative charge. And we want our element or our atom of that element to have a total charge of 0, to be completely neutral. So whatever this number is here, that is going to be the number of protons and therefore the number of electrons. The second number that you see is the atomic mass. That mass is the number of protons plus the number of neutrons. And that is going to be shown below the symbol. So here we have 12.011. That is the number of protons and neutrons because they are the things that have an atomic mass unit of 1. And we'll talk about this 0.011 a little bit later, but just know this is your atomic number. This is your atomic mass. So like I just said a second ago, we want to know the different numbers of subatomic particles. How do we figure that out? Well, our proton number we know is the atomic number. And as we said before, the electrons are the same as the number of protons. So if you know the atomic number, you know protons and you know electrons. How do you find neutrons? Well, you just take that atomic mass and subtract the atomic number. And if you like math, I love math, but some people don't, and that's okay. If you like math, this is the formula that your book gives you that you'll use in chemistry. But essentially, what it says is protons plus neutrons, right? That's your atomic mass. Subtract the number of protons. That's your atomic number. And it will give you neutrons, right? Basic algebra. What that ends up looking like, for example, sodium. If you look at it on the periodic table of elements, you'll see that the atomic mass is 23, about, we round, and the atomic number is 11. So we take 23 minus 11 and we get 12 neutrons. So let's do a little bit of practice with these elements here. And this is a great time if you grab a piece of paper, or maybe you're good at doing it in your head. That's great. Feel free to pause the video. But we're looking at carbon, we're looking at sodium, and we're looking at oxygen. And we want to know the number of protons, the number of electrons, and the number of neutrons that are found in these three elements. So go ahead, pause. I'm just going to keep moving through the slides. Do your math here, and then let's go to our answers. Okay, for carbon, we have 6 protons, 6 electrons. Remember, it's the same as protons, so it's 6. And then neutrons, we took 12 minus 6 to get 6. Sodium, we have 11 protons, 11 electrons, and then we took 23 minus 11 to get 12 neutrons. And then oxygen, we got 8 all the way across. 8 protons, 8 electrons, 16 minus 8, and we get 8 neutrons. If this worked for you and you figured it out, this is awesome. You're good to keep moving on. If you struggled here, on the D2L shell, there are some worksheets in the extra resources. You don't have to print them out. You can if you want to and have access to a printer, but it helps you to practice using the periodic table, doing the subtraction, finding the mass number and the atomic number. So feel free to do as much extra practice as you need. Anyone that is wondering, if you are given a quiz or an exam, you will either be told the atomic number and the mass, or be given a little box like would be on the periodic table, or you'll be given a whole periodic table. You will not need to memorize any of this. So just know that that is available if you need it, and calculators are available if you need them for any exams or quizzes. There'll be a little pop-up on your screen for them. Okay, so why did we see something like 12.011 for our mass, right? That doesn't make a lot of sense if we know that there are, a certain number of neutrons. Well, we need to talk about something called isotopes. Isotopes are elements that are all the same, right? It's all carbon, or it's all hydrogen, or it's all whatever, because it has the same number of protons, but there is a different number of neutrons. And your book talks a lot about carbon 12, carbon 13, and carbon 14. And if we look at this graphic here, you'll see this is our normal carbon that we think about as our everyday stuff, like, in your pencil lead and in your body. When we look at carbon 12, we see that it has 6 protons, 6 electrons. We have that atomic mass of 12, so 12 minus 6 gives us 6 neutrons. This is carbon 12. But some of that carbon that we find in the world is carbon 13. It has 1 extra neutron in this nucleus. So when you look at it, there'll be 7 neutrons, which is different than carbon 12, but it's still carbon because the protons are the same. Okay, the proton is really what defines an element as that specific element. And then carbon 14, which we use in radiocarbon dating, so finding the age of old stuff like fossils, it has 8 neutrons. So when we look at it and count those subatomic particles, we get 8 neutrons. But because it still has 6 protons, it's still carbon. So in order to get that atomic mass, we have to take an average of all of these isotopes. So we add up, not we, but it's been added up all of the times we see carbon 12, carbon 13, carbon 14, whatever. And then, an average weight comes out to that 12.011 atomic mass units. So, what does that mean exactly for us? Why did we do all of this math? Why do we care about isotopes? What's happening? Well, we want to know what that atom looks like because what it looks like, its structure, determines how it reacts. So, we can make this shell model. So an atom has shells or orbitals of electrons around its nucleus. Each shell can only hold so many electrons before we need to move out and make another shell. We have our nucleus, and the shell that is right around that nucleus can only hold 2 electrons. That's it, just 2. Once we fill that shell with 2 electrons, then we move out and make another shell. And that shell can hold up to 8. We call this the octet rule, that it has to hold up to 8. It cannot hold more. It can hold less. It cannot hold more. And then, of course, we fill that shell up with 8 before we move on to the next one. So for example, we've got our atom here that we know has 8 protons, 8 neutrons. So we've drawn that as our nucleus. Because we have 8 protons, we know we have 8 electrons. So what happens is we fill our first shell with 2. That is going to leave us then with 6 more electrons that need a home. So we'll move out an energy shell and we'll put our 6 electrons there. 1, 2, 3, 4, 5, 6. And again, on our D2L shell, there are extra resources if you want more practice in drawing out these electrons and where they go in the shells. It's not a huge component of things you'll have to do, but there are questions about this on your quizzes, on the exam, on the final exam. So we want you to be comfortable in doing this. So again, we fill up that shell, the first shell with 2 electrons, any other shell with 8. And that is going to tell us basically how chemically stable or not our elements are. Elements will gain or lose or share electrons in order to get to that magic number of 8 electrons. And that outer shell is called a valence shell. And so we call that whole thing the octet rule, that getting to 8 electrons or 2 if it's a small atom, we want to get there to make the most stable chemical compounds. So to share or to give or lose those electrons is a chemical bond. So let's talk a little bit about these bonds. There are 3 major types of chemical bonds. The first one is an ionic bond, and that is shown here by our sodium giving away an electron to chlorine, and chlorine is going to take that electron. So that is an ionic bond. We're going to actually give away that electron to another atom, which will take it. Then there is what we call covalent bonds. That's this up here, where we're sharing those electrons. And if you've never seen these kind of structures before, every place that there's a line is showing a carbon. And then obviously where there are other symbols, those are those other elements. But these are all sharing electrons. And then we have what is called a hydrogen bond. And this is very important in the human body with water because there's these very weak attractions to these slightly charged parts of the molecule. And we're going to dive much deeper into all three of these bonds. But here is an example of that hydrogen bonding. Okay, so bonds. What do you make with a bond? You're going to make a chemical compound. So a chemical compound just means that there is a bond between two or more elements. And we can classify this as a ionic compound or a molecular compound. Ionic compounds have ionic bonds. Molecular compounds have those molecular bonds or, oh goodness, covalent bonds. Let's start with ionic bonds. You're going to make ions when you have ionic bonds. So basically, an atom that has a positive or a negative charge is an ion. And the way that we make these is that it is produced by losing or gaining electrons. Again, electrons have a negative charge. So if you gain an electron, then you are negatively charged. If you give away or lose your electron, then you are positively charged. We give these ion special names. An anion is the negatively charged, and I like to think anion, a negative. So if that helps you remember, great, use it. If not, throw it out. But anions are negatively charged. And then cat ions, I like to remember the T in cat ions looks like a plus sign. So cat ions are positively charged. So this kind of shows you here, we've got our sodium. Overall, it's going to have no charge, right? Because it has the same number of protons in its nucleus as electrons in the orbital clouds. However, sodium wants to get 8 valence electrons. It has an extra one here in this little cloud that it has, this orbital. So it's much, much easier to give away 1 electron than to get 7. So it's going to give away that 1 extra electron. When it does that, now it only has 10 electrons, so we have a positive 1 charge. So essentially here, if it's neutral, but it loses an electron, it becomes positive. When it's neutral, then it gains an electron, it becomes negative. So how this then works out is that you give away, or you're an atom that accepts the electron. And when that happens, you have these positive or negative charges, which make those atoms attracted to one another. And when we have this, we form what we call a salt. And a great example is sodium chloride. That's table salt. You know, it's what you put on your French fries or whatever. It's around you, probably in your home today. So how it works, sodium gives away its 1 electron to chlorine. If we looked at chlorine, it just needed 1 more electron in order to get 8 in its valence shell. And it's much easier to take in one electron than it is to get rid of 8 of them. So it's happy to accept sodium's 1 electron. Once that happens, sodium becomes slightly positively charged, right? +1. Chlorine got an electron, it becomes negatively charged, -1. Because of these positive and negative charges, they are attracted to each other and they make this crystal lattice, this nice orderly structure that we know of as table salts. Okay. Okay, so let's move on to sort of the opposite of ionic bonding, which is covalent bonding to make molecules and molecular compounds. So, covalent bonding is when we share the atoms of those 2 or more different elements. And we call that thing that we make a molecular compound, which would be something like carbon dioxide, right? Because we've got carbon and oxygen that we are combining together. If it's the same elements or like same atom or 2 atoms of the same element, then we call it molecular whatever the thing is. So molecular oxygen, for example, is 2 oxygens bonded together, where a molecular compound is 2 different types of atoms. Very small distinguishing thing, not really the end of the world, but if you end up taking chemistry courses, then it will be something they stress very much to you. So might as well get it now that a molecular compound are 2 different kinds of atoms. Molecular, whatever the thing is the same type of element bonded together. Okay, so in order to show these different kinds of bonds, we need chemical formulas. And there's really 2 main ones that we'll use. We can have the molecular formula, which tells us the type and number of atoms. For example, carbonic acid, we would write it as H2CO3. The H being for hydrogen, it's what we would see on the periodic table. And this little subscript of a 2 means that there are 2 hydrogens. And then, of course, a carbon, and then an oxygen. And this little subscript of a 3 means that there are 3 oxygens. Benefits to this molecular formula: it's concise and it tells you how many of each kind of atom there are and what types of atoms, what elements are in this thing. Problems: it does not show you where these things are, which is why we also have this structural formula. That is going to show the number and type of atoms and how they are arranged. So for example, carbon dioxide, if we write it out structurally, would be O, this double bond. I know it looks like an equal sign, but it's a double bond. Carbon, double bond, oxygen, and we call that carbon dioxide. Pros to this: you know exactly where those atoms are, so you have a good idea of how it reacts. Problems, though, it's long, especially if you have a lot of different atoms involved in the formula. But it will show us either one, sort of where these covalent bonds are at and how we look at them. So if you've got a single covalent bond, that means that we are just sharing 1 pair of electrons. And that's sort of our top picture from your textbook here. Hydrogen gas, right, that would be molecular hydrogen really, is 2 hydrogens bonded together, and they are sharing this pair of electrons. And we designate it with just 1 line, like a little dash saying a single bond. A double bond is going to be sharing 2 pairs of electrons, or 4 total electrons. And that would be like O2, oxygen gas. So we would have our oxygen here, we have our oxygen here, and it's sharing 1, 2, 3, 4 total, or 2 pairs of electrons. And we would draw that out structurally by showing a double bond. So O, that 2 dashes, or what looks like an equal sign, double bond. Then a triple covalent bond is sharing 3 pairs of electrons. And an example would be N2 nitrogen gas that is sharing 3 pairs, or 6 total electrons. And so we can see here nitrogen and nitrogen, 1, 2, 3, 4, 5, 6 total electrons are being shared. And we would draw that out as N, 3 lines, or like an equal sign with a dash over it, to another nitrogen. Covalent bonds can either happen when an atom equally shares, so that it is having no charges, or there can be what we call a polar covalent bond, where they do not share electrons equally. And that happens usually when one of those atoms in the bond is bigger than the other. So it has more of a pull on those electrons. So, for example, non-polar covalent would be like 2 hydrogens, right? And they're playing tug of war. They both share the electrons equally because they're both equal in their strength to pull the electrons. Polar covalent would be something like chlorine to a hydrogen. Chlorine is much larger than hydrogen. If we look at how many protons it has in its nucleus compared to hydrogen. So it is stronger, it's bigger, it has more pull on our tug of war rope to pull the electrons towards it. So here is some more examples, right? Like a non-polar bond of oxygen, they share these 4 electrons equally. Whereas something like water, oxygen is more what we call electronegative. It has a stronger pull compared to hydrogen. Because of that stronger pull, it's going to keep those negatively charged electrons closer to it, giving it a slightly negative charge. Whereas the hydrogens can't pull the electrons to it as much, so it's going to have a slightly positive charge. And that slight negative or slight positive charge is what we know as polarity, or a polar bond. We also want to look at what we call amphipathic molecules. These are usually large molecules like this phospholipid that have one side of them being polar, so that unequal pull of electrons, while the other side is non-polar, so there's no difference in how it shares electrons. The part that is polar is what we say hydrophilic. It likes water. It can interact with water. Where the non-polar part is hydrophobic. It's afraid of water. That's what hydrophobic means. It will not interact with water. A great example in biology are phospholipids. They make up cell membranes, and they pretty much form this double layer, with the outsides being polar and the insides being non-polar. So that is how we make a cell membrane, right? The outside and the inside can interact with water. This middle layer does not. Last but not least is this hydrogen bonding. It can form between 2 polar molecules. Again, that polarity means that there's a slight positive and a slight negative charge, and that allows the slight negative or slight positive charge of another molecule to be attracted to it. Individually, these slight attractions are weak, but collectively it's strong, and that's why water behaves the way that it does. So this oxygen is slightly negative. It has this slight attraction to the hydrogens that are slightly positive. And we can see that throughout the arrangement of these molecules. And again, individually, this is weak and it can break apart. But collectively, it makes a very strong sort of interaction. Which leads us to water. Let's chat about water specifically. Of course, we know that water is going to be about 2/3 of human body weight, right? That's when we looked back at our chart, which elements are in the human body. Oxygen and hydrogen are high on the list because of water. We know that we've got a polar molecule because we've got one oxygen atom bonded to two hydrogen atoms. That oxygen is larger, it pulls the electrons towards it more than the hydrogens. So we have oxygen as the partially, slightly negative charged part of our molecule, and hydrogen as the slightly positive part of our molecule. What does water do in the human body? It acts as a transport. So any substance that is dissolved in water can easily move in the body. It acts as a lubrication because it decreases the friction between body structures. It acts as a cushion. It's able to absorb sudden force and the movement of the body. And it helps us to excrete waste. So any unwanted or harmful substances that can dissolve in water can easily be eliminated. What makes water so special? Well, it has several properties that come with being a water molecule, which help it do its jobs of lubricating, elimination, absorption, and that stuff that we just talked about. So the first being cohesion. That's the attraction between water molecules due to hydrogen bonding. So cohesion is two water molecules sticking together. Then there is adhesion. That's the attraction between water molecules and a different substance. Also, because of those hydrogen bonds most of the time, but it is the ability for it to stick to other stuff. And you can think of it in like Bio 102 of, sticking to leaves and that xylem and phloem. But in a human body, it's like sticking to the capillaries and veins and arteries so that it can move along those structures. We also have surface tension. That's this sort of inward pulling force of water. And you can do this at home if you want. But if you get a penny and an eyedropper, you can see how many drops of water you can actually put on a penny before it spills. And you'll make like a little bubble of water. And that's because of that surface tension. In a human body, it's what causes like the moist sacs of air in your lungs. We call them alveoli to be able to collapse and inflate. So we've got that. We also can use a suffocant, which is a lipoprotein, to stop that collapse. So if you are ill and you're coughing and you've got this, sort of moist mucus in your lungs, you want to expel it. That is what is in Mucinex, for example. And it's because of this tension. And here we've got this little water strider. It's a little water bug. It can sit on the top of a pond or a puddle and move around because of the surface tension. So just a little humor to break it up here, right? Cohesion, sticking together of the water molecules, adhesion, sticking to other stuff, and then surface tension is that sort of ability to hold things up or to have this, sort of film on the surface because of this attractiveness inward. So it can hold up bugs. What else is so cool about water? It has a high specific heat, and that's the amount of energy required to increase the temperature of 1 gram of a substance by 1 degree Celsius. And water has a high specific heat. There's a lot of energy needed to raise the temperature of water 1 degree. Imagine, like, you want to make spaghetti, you have a pot of water on the stove. It takes a while for that pot of water to heat up to boil. Or imagine you want to go swimming, even in the ocean. Here in Charleston, in April, the water is cold. It takes it to be about July for it to warm up where you want to go in the water. At least for me, I'm kind of a baby about cold water. We also have a high heat of vaporization, which means that it takes a lot of energy in order to turn liquid water into a gas or a vapor. So when you sweat, essentially what's happening, that liquid water is turning into a water vapor, and leaving your body, evaporating off of your body, takes heat with it, so it cools your body down. Water is also called a universal solvent. And what that means is that water is great for making a solution. Solutions are just these special kinds of mixtures that includes a solvent and a solute. Solvent is just the thing that's in the bigger amount. Solute is the thing in a lesser amount. So if you're making a solution of salt water, for example, the solvent was water, the solute is the salt. And water is the solvent that is in our body. It's what is, in the greater amount to make a solution of other elements. And so the solute will dissolve in water, and many, many substances, most of the ones that we need in our bodies, will dissolve in water, which is why it is called a universal solvent. There are some exceptions in this. Substances that dissolve in water are going to be polar molecules and ions. And so we call those hydrophilic, means they are water loving. And those things that will dissolve, we also know them as electrolytes. So if you're looking at like Gatorade or Nun tablets that have these electrolytes, if you actually read what they are, they're usually salts, and they break into those ions and polar molecules. Then there are substances that don't dissolve in water. Those are nonpolar, and they're hydrophobic, or they are afraid of the water. Those are non-electrolytes. They do not dissolve. What do we mean by this, like dissolving and disassociation? Well, it's just separating the ions in an ionic compound by this polar water molecule. And again, we call these substances that are able to break apart electrolytes. And they get that name because they can conduct electricity. Like if you put an electric current through it, it will move the electric current. And table salt, NaCl, that is the major salt that will break apart in the body, and it is in your blood plasma, or the fluid part of your blood. Molecules that do not dissociate, again, are non-electrolytes. So an example is like a fat, or some vitamins. They do not dissolve in water, and what will happen is they'll all kind of stick together in this non-polar area, and this space right here repels the water away from it. We call it a hydrophobic exclusion zone, so it does not interact with water. At the same time, if we've got an empathic molecule like a bile salt or like a phospholipid, they'll stick together. The bipolar areas will join together, and then the polar part of it will interact with water. And that's what's happening here in this last little picture from your book. Okay, maybe a great place to pause for you if you would like to, because now we're going to switch gears a little bit and talk about acids, bases, pH, and buffers. So feel free, pause the video here, or keep going, diving on in. pH, what is that? That is a measurement of the hydrogen ions in a solution. And it's a logarithmic measurement, which is just a fancy word to basically say that every time we move on this pH scale, we're moving up not in units of one, like, 1 to 2. Usually that means there was one thing and now there's two things. But if we move on a logarithmic scale, there are basically for us in pH 10 times more of the thing as you move. So if we go from 0 to 1, that is 10 times the amount of hydrogen compared to just going, 0 to 1 in a counting scale. Anyway, not that important. Just my chemistry brain goes to this. Anyway, the range of pH goes from 0 to 14. Anything on the pH scale that is from 0 to 6.9999999 is considered acidic. Anything that is 7.001 through 14 is basic or alkaline, and anything that has a pH of 7.000 is neutral. And the only thing that is neutral is pure water. So there, are many products out there in the market to filter tap water, like the what is it, pure filters or zero filters, and a lot of them come with little tester strips or a little device, and you get your water and you look at the parts per million dissolved in it. If there are 0, that is pure water and it is neutral. Okay. As you are looking at the pH scale, as you increase the amount of pH, so as you go from 0 to 1 to 2 to 3 all the way to 14, you are actually lowering the amount of hydrogen. So the most hydrogen is at something like 0 in battery acid or 1 in your stomach acid. That has a lot of hydrogen. As you move up to, baking soda, there is much less hydrogen ions. If you look at the pH decreasing, or I'm sorry, if you're looking at the pH increasing, you are decreasing the hydrogen concentration. So lots of hydrogen over here, very little over here. If you are someone who has taken chemistry before, and you maybe remember, there is a pOH scale as well. It's the opposite of the pH scale, but that is not something that we are really going to dive into. But if it helps you to sort of think of it, you've got a lot of hydrogen on the low end of your pH scale, not a lot of OH. Opposite, if it's very basic or alkaline, you've got a very small amount of hydrogen, but you've got a lot of OH. Okay. So, what does this all mean? If something is acidic, if it is an acid, when it breaks apart in water, it's going to make hydrogen ions and some other negative anion. Because of this, we call an acid a proton donor. Hydrogen has one proton. So if it is breaking off of a substance, we are donating that proton. As we add this proton donor, this acid, to water, we are going to increase the hydrogen concentration in that solution So we will have a low pH, anything less than 7. A base, on the other hand, is something that will accept hydrogen when we put it in solution, or there'll be a lot of OH. So we call it a proton acceptor. Because there's a lot of OH, it will react with this hydrogen and it decreases the hydrogen concentration. So we call things that accept that hydrogen, take it in, alkaline or basic. And that's things that have a pH bigger than 7. Neutral is when you have an equal concentration of H and OH concentration. That's water, right? The hydrogen with the hydroxide mixed together to make water. But water, as you know it and love it, doesn't really stay as H2O in a solution. It's going to be these hydrogens and hydroxide ions. Again, not super duper important to get into all of the nitty gritty details, but just knowing if you have equal hydrogen and equal OH concentrations, you're neutral. You have a pH of 7. So, what is neutralization and what are buffers? Neutralization is when you have something that is acidic or basic alkaline and you bring it back to being neutral. How do you do that? Well, you have acids being neutralized by adding a base, and bases are neutralized by adding an acid. Essentially, if you add an acid to a base, you will get water. I do not recommend doing this in your home at all. Do not. It's a violent reaction if you've got a strong acid and a strong base. So don't do it, but you will end up with water. This is how medications that neutralize stomach acid, like if you've got heartburn or you've got like a gurgly tummy, that's what it's doing. You're adding this antacid, which is basic. It is going to then lower or I guess increase that pH because it is neutralizing it. It's making essentially water. Buffers, similar, but they're there to sort of prevent large changes in pH. So it's a substance that you put into your solution that if extra acid or extra base is added, it is going to accept those hydrogens from the extra acid or donate a hydrogen to the extra base and keep that pH scale from really moving in any direction. We're going to keep the pH where it is at an optimal range. A great example of how this works, carbonic acid is a weak acid and bicarbonate is a weak base. And both of those are found to buffer the blood pH. So your pH in your blood should be around neutral. It'll be slightly basic or slightly acidic. That's okay. But if it gets too acidic, you will die. If it gets too basic, you will die. So your body has a way to use carbonic acid or bicarbonate to sort of keep this normal pH of about 7.35 to 7.45, depending on, your activities, what you eat, if anything is wrong and you have a disease, that's what those are for. And you want to maintain that critical range because if you go outside of it, obviously you'll have alkalosis or acidosis, and if it gets much outside of that range, it can lead to death. Okay, let's talk about water mixtures. A mixture is just any combination of two or more substances. And pretty much these substances are mixed together, but not chemically changed. There's no chemical reaction that happens. So you can filter out or sort out a mixture by physical means. So think of like trail mix. That's a mixture, right? You could take out the raisins, take out the M&Ms, take out the peanuts, and do that, by sorting it. This cup of tea that is here, you could evaporate or filter, and you could get the water separated from the tea that is in there. With mixtures, we have to sort of look more closely at what is in them in order to categorize them. You can have a suspension. That's when you've got large particles mixed with water. A great example is your blood cells in the plasma or sand in water. And this is an experiment, you could very easily do at home if you want to see it in real time. Get some sand, get some water, mix them together. For a while, it'll be a nice little cloudy mixture with the sand floating around. But if you let it sit still, the sand will sink out and the water will be on top of it. And it will not stay mixed unless you keep it in motion, which is again why if you get blood drawn to do tests, they'll put it on a rocking machine to keep your blood moving. Blood banks will do that once they thaw out blood because they want to keep it in suspension. And if you pass light through it, the light will scatter and the objects or suspension will look cloudy or even opaque. You can't see through it. A colloid is smaller particles, but they are still suspended in the water. So an example is you've got fluid in your cell cytosol and fluid in your blood plasma, and there are tiny-ish things that are in there, molecules that would settle out if it's not in motion. When you put light through it, that light will scatter. So it'll sort of look cloudy as you shine a light through it. A solution is a homogeneous mixture. So when you put something in water that dissolves like salt or sugar, and you can't really see with your eyes to pick it apart, okay, that is a solution. And light will not scatter. You can shine a light through it, and it doesn't really settle out of the solution. In order to get it to separate, you have to do more physical means, like evaporate the water out of the water solution. Great examples, again, sugar water, salt water, but your blood plasma is also going to have solution of salts in it. So this comes from your textbook, sort of just showing you suspension. When it's in motion, you've got blood like we know it, but if you let it settle, you have red blood cells, white blood cells, and the plasma. A colloid, they want you to think of it sort of like Jello. So there are smaller solutes, like some other macromolecules in there. And then a solution, like the salt water, think of it like pop or soda. There is another category that doesn't really matter to us a whole lot, but your book talks about. It's called emulsion, and that is two substances that really don't dissolve. They don't want to work together, but if you shake it up and keep it in motion, you'll have some blobs mixed together, and that's like oil and water, or like a Italian salad dressing. Okay, so why did we just do all of that chemistry for like an hour? And that was to look at these biological macromolecules and how they are working in the human body. So some of this might be review still from your intro bio classes. Some of it is going to be more in depth. So feel free, pause this video now, take a break, stretch, get some snacks, because this is really the most critical part for understanding as we move forward in anatomy and physiology. Of course, we know that there are biological macromolecules. They are large organic molecules made by the body. And these are organic molecules. So they're going to contain carbon. They also contain hydrogen and oxygen. There are 4 major classes: lipids, proteins, carbohydrates, and nucleic acids. Some very important terminology that you may already know, but that you need: polymers. Polymers are just these repeating subunits stuck together, and that is what a polymer is. So monomers are those individual subunits. What I mean is that a carbohydrate is going to a carbohydrate is going to contain monosaccharide monomers, so single sugars. And that's going to happen over and over and over to make the polymer that will make the whole carbohydrate. Nucleic acids have nucleotide monomers, and proteins have amino acid monomers. So those monomers make polymers that make our macromolecules. In order to create these macromolecules, we also need to synthesize them, but we would want to also break them down. So in order to make them, we have a process that we call dehydration synthesis, also sometimes called condensation synthesis or just condensation. What happens is that there will be a biomolecule monomer being connected or bonded to another monomer. And when we do that, water is pulled out of that reaction. Water is made. So that's our top picture here. We've got our monomer and our monomer. They have these little tail part here that are going to react with one another. And when we react this and this together, we get water. And now we have a bond of these 2 monomers to make our polymer. The opposite process of dehydration synthesis is hydrolysis, also called hydrolysis, lyse meaning break. That is going to break apart these biomolecules by adding water to it. So what happens is you have this macromolecule being made here. You add water and we break apart this bond. The other word that is not on this slide but is in our picture is dimer, and that just means 2 of these monomers bonded together. It's not that important, but in case you're wondering. But again, dehydration synthesis, creating our biomolecules, and we produce water. Hydrolysis, breaking apart our biomolecules with water. So let's look at lipids first, or fats, right? And here is what this carbon skeleton chain really would look like. And of course, it's in meats products that you eat. It's in all the food we eat, really. But here's what we got going on. Lipids are important because they store energy. They're in our cell membranes, and hormones are also lipids. There's really 4 primary classes of lipids that we want to talk about. First, we've got triglycerides, then phospholipids, steroids, and eicosanoids. So triglycerides, those are used for long-term energy storage. They're going to be the most abundant lipid that we find in the body. They're formed from glycerol and 3 fatty acids. That's their monomer. And the fatty acids vary in length and the number of double bonds. So we can look here and see, here's a double bond. double bond, but here's all single bonds. So where and how many of those double and single bonds make our different kinds of fatty acids? If you have a saturated fat, that lacks double bonds. There are no double bonds. Unsaturated fats have at least one double bond, and then the polyunsaturated has many double bonds. The way you can remember this, or that I do anyway, saturated, there are no double bonds, so there are totally filled up with these hydrogens. There's no more space to connect anything, right? Totally saturated. Unsaturated, we've got this double bond, so we're missing hydrogens. It's unsaturated with hydrogen. And then polyunsaturated, there's just a lot of those double bonds. Phospholipids, that's going to be very important to make the lipid bilayer of our cells. The way that it's laid out is similar to a triglyceride, except instead of those 3 tails, it's going to really have 2. We've got this hydrophilic head portion that is polar, that can interact with water. We've got hydrophobic tails that group together that are nonpolar, that do not want to interact with water. And then, of course, when it's a layer, the other side of it would be also that hydrophilic. And it's got a phosphate group. So there's phosphorus. And you can see that if we zoom in, that phosphorus is in that hydrophilic head portion. Steroids are going to be composed of carbon rings. It's in a series of 4 of them fused together. But these side chains are what extend off of it and make it different from other 4-ringed structures. The major player that we're going to talk about is cholesterol. That is going to be in animal plasma membrane, so in the cell membranes, and it helps keep that lipid bilayer kind of flexible and movable, but still strong and together, especially under temperature changes. So it's very important in the membrane. We also have steroid hormones like testosterone and estrogen that are obviously important in sex signaling, basically, secondary sex characteristics. And then bile salts, which help dissolve things that are not really wanting to dissolve in water into our body, which is mostly composed of water. Okay, carbohydrates are next, and you're probably very familiar with these. A lot of fad diets sort of exclude carbs, but they are important for your body to function. So let's talk a little bit about carbs. Carbohydrates are made up of monosaccharides. Those are our simple sugars, glucose, fructose, and galactose. Disaccharides are when we synthesize 2 monosaccharides together. A great example, sucrose, okay? And then polysaccharides, that's a whole bunch of monosaccharides together. And a great example of that is something like starch. It's a lot of glucose molecules put together. Glucose is going to be the most common monosaccharide that we find. We need it to help our bodies make ATP, which is where our cells get their energy source. And of course, the concentration in a human body has to be carefully maintained. You do not want to have too high of a sugar, and you don't want to have too low of a sugar. So obviously, a medical test that is done when people come in and they are sick, it can be a blood glucose reading. This is especially important if people have diabetes and type 1 or type 2, depending on if the body can make insulin. You may need to get insulin if your sugars are too high. And then we have ribose and deoxyribose that are found in RNA, DNA, and ATP. We also have our polysaccharides. The most important that we're going to find is glycogen, which is common in animals. Extra glucose that we have in our body after we eat a meal or, have something sweet, whatever it is, extra glucose gets stored in our liver and our skeletal muscles as glycogen. In plants, we'll have starch and cellulose. That is how they store that extra sugar. And really, it's not important that you know these structures, but they're here in case you're interested. Amylose is often found in fungi with some other things as well. Starch, here's an example of that. Here's glycogen. It's just a lot of these glucoses all stuck and branching together. And then cellulose is this same thing with a lot of glucose, but in a more orderly instead of branch pattern. Okay, let's dive into our nucleic acids. Nucleic acids are used to store and transfer genetic information. They have the monomer of a nucleotide, but of course they have a sugar, a carbohydrate as well, creating the backbone for these nucleic acids. That sugar is ribose or deoxyribose. Ribose for RNA, deoxyribose for DNA. We've got to have a phosphate group. So that's our phosphate group. And we've got our nitrogenous base. So that is going to be these ring structures with nitrogen. There are two main types of nucleic acid. We've got deoxyribonucleic acid, which is DNA, and we've got ribonucleic acid, which is RNA. Let's look at DNA first. DNA is double-stranded, so there are two strands. They run anti-parallel, which means if we're looking at this sugar like a little house, one is pointing upwards, the other side points downwards. Not super, super important right now for us, but will come up later. It has a helical shape, which means it's sort of like this spirally staircase look to it. And it's how we store genetic information and serves as a template in order to replicate. Double strands are held together by hydrogen bonds. That's between these nitrogen bases. And there's always going to be this pairing. There's going to be thymine pairing with adenine, so A with T, guanine pairing with cytosine, or G with C. And this is review or should be review, but that is happening here, and that's what makes our double helix. RNA is a single-stranded nucleic acid. We find that in the nucleus of cells as well as moving out into the cytoplasm of the cell. We have a ribose sugar, a phosphate, and there are 4 nitrogen bases. They are similar to DNA, except instead of thymine, we have uracil. So we've got adenine pairing it with a guanine on the DNA. We've got back that up. We've got adenine, guanine, cytosine, and uracil. How this works is instead of a thymine in our RNA, we have uracil. So this uracil would pair with the adenine of DNA. We've got adenine pairing with thymine of DNA. We've got cytosine pairing with guanine, guanine pairing with cytosine in order to make that RNA strand. And that is part of our transcription and then later translation in proteins. So if you're interested in all of that, that's review from 101, but we talk super briefly in just a moment as well there. ATP, that's going to be a nucleotide that has the base of adenine plus a sugar and then 3 phosphates bonded together. Those phosphates don't really like being bonded together, so those bonds break apart. When it breaks apart, we get this energy that is released. So this is what our cells use as their energy currency. Proteins, our monomer is going to be amino acid. There are 20 different amino acids found in living things, and they are linked together by peptide bonds. Even though there are only 20 amino acids, the order in which we have those amino acids is what makes a different type of protein. Proteins have a lot of functions. Again, they're going to be catalysts or an enzyme to make metabolic reactions happen. They are defense. They transport things. They're structural support. They allow for movement. They are regulatory, and they provide storage. So we need RNA in order to then make a protein. We get a template from our DNA to make our RNA, then we use RNA to make our proteins. When we do this, we start with a primary structure, which is just the linear sequence of amino acids. It's just what order are those amino acids in. The secondary structure is a little bit modified. It's where we get some folds or twists to make an alpha helix or a beta sheet. That's just these sort of complexes held together with hydrogen bonds. Then we go to tertiary structure. This is where we start to sort of bend and fold and make a 3D structure for our protein. And we can get two categories. There's globular proteins, which are really just like a blob. They're compact, they're spherical, and this is really what they look like. A bunch of these beta sheets, alpha helixes, all interacting in a blob. Great examples in the human body: antibodies, hormones can look like this, and enzymes. Then there are fibrous proteins that really are extended, elongated, and strand-like. In your body, you've got keratin, elastin, collagen. All of that is really found like in your skin and connective tissue. And then there are some other contracting fibers and like your hair, the structure of your fingernails, all of that is these fibrous proteins. And then there's quaternary structure, which is present in proteins that have more than one polypeptide chain. And so it's just really these different peptide chains sort of forming a structure together. An example: hemoglobin, which is in your blood to carry oxygen and carbon dioxide, that is going to be with these 4 peptide chains all interacting together. Denaturing a protein is when we break apart those structures, and then the protein is no longer usable. So if we change its shape, we change its function, and it's usually irreversible. And this is one reason why fevers are dangerous to the human body. If you are heating up the human body, you have the potential to denature proteins, and those proteins are involved, in structure and transport and defense, in all of the things really that your body needs to function. And like we said, it's usually irreversible, and it can occur because of temperature change, pH change, or mechanically breaking it apart. So this picture here just shows you like shrimp. If you go catch them in the ocean and get shrimp and they're fresh, they're usually this like whitish color. But then when you cook them, heat them up, you break apart some proteins, denature them, and then they turn like pink. If you are looking at an egg, same thing, like this albumin and this yolk, okay, all of the proteins that are in there. When you heat it up, then you are denaturing it and it becomes like a fried egg. You can mechanically do it. If you take the egg yolks and you beat it, and you keep doing that for a while, then you're going to get meringue, right? You're going to get this frothy, fluffy stuff because you've denatured the protein. If I took any of these things and I changed the pH of their environment, same thing, I would denature the protein. Okay, so that is the end there. Of course, you've got your homework, you've got extra practice, you've got videos, resources on our D2L. Please feel free to contact me with any questions, come to office hours, write in the discussion post. All of that are great places to get some extra help if you need it. Again, a lot of this probably feels like review because it is, but if you have questions or need help, please reach out. I'm happy to do that. Otherwise, thank you for listening to our video here, and stay healthy and stay well. And I will talk to you guys again soon. All right. Bye, y'all.